Of course, we are very happy to have Antoine Mellet giving a talk for us here. So Antoine will talk about free boundary problems for cell motility.
Thank you, Inwon, and thank you for the invitation, and thank you everyone for attending the talk. It's great to see so many people I haven't seen in a long time. I guess we see more people even now that we don't give talk in person. And so I'm going to be talking about some work that I started with a colleague in Paris, Nicolas Meunier, and completed largely with a student, Alessandro Cucci. And then some of the results also were proved more recently with Yijing Wu, who's a postdoc here at Maryland. Let's see if I can change slide. So the basic thing that we were trying to do was come up with a relatively simple model to describe cell motility. So cell motility is an important feature in biology that is fairly complex and that is still being researched. And so here you have a little movie that shows sort of what we're after, and here are more movies. And the basic idea, especially if you look here at the first movie, what you see is a cell that is moving. You have some kind of outer boundary of the cell. So it's moving on a substrate. So it's really a 2D, it's really meant to be a 2D model. The cell is moving on a substrate. And you see that you can really define a kind of boundary of the cell that is moving. And the idea is that the motion is determined by two very opposite mechanisms. One is close to something like surface tension, and it keeps the cell together. And the other one is what you can see developing all those protrusions that comes out, and that's really what's causing the motion of the cell, right? The other aspect that we're interested in, and some things you can see on the other two movies that, let's see if I can restart the movies. Yes. So if you look now at the next two movies here, what you see is a cell that seem to be moving in a fairly consistent manner in one direction. And that's also an important feature of cell motility, is this idea that cells seems to be able to self-polarize. The cells that might even start being very symmetrical at the beginning may suddenly develop a front and a rear and start moving for a long period of time in a given direction. And mathematically, this would be the existence of some kind of traveling wave-like solutions. Okay. So a lot of people have investigating this. I mean, biologically speaking, it's a very complex thing. And what we're aiming at is just a simple mathematical model that could describe those phenomena. The magic word that you'll see a lot in papers that have to do with this problem is actin cytoskeleton. So actin is a kind of polymer that forms a rigid network inside the cell, and it's a polymerization. So this thing is constantly polymerizing, and that's what is creating those protrusions. That's when you see the membrane of the cell shooting out. That's what's causing it. And at the same time, it's depolymerizing inside the cell, and there's a constant source of energy, right? This polymerization requires energy, so it's an active system, and those protrusions are responsible for those instabilities that make the motion of the cell interesting. Now, what we start with is a very simple model. I mean, this variants of this model have been proposed in different papers, but what we look at is this simple model here. That's so first we have a density rho, which will describe kind of everything that's going on inside the cell. So the actin cytoskeleton, but also all of the other things that are inside the cell, with the idea that rho should be more or less 1 inside the cell and very small outside the cell. And so rho tells you where the cell is. And the cell is moving with a certain velocity v. So you have this continuity equation here. And v is the velocity v is the result of two things. So one is they call it osmotic pressure. It's something that keeps the cell together. It's this typical pressure that you see, right, coming out of Allen-Cahn or Cahn-Hilliard equation. We know that this is going to give rise to some kind of surface tension. W is a double well potential that's going to, so typically rho square 1 minus rho square, right? So that with the two well at 0 and 1. And so we know that when epsilon is 1, this is going to keep the cell together and create some kind of surface tension mechanism. And then the other one that's important is this gradient phi, right? So minus gradient phi is a force that comes from this polymerization of the actin that pushes the cell outside. And usually this phi is interpreted as a concentration of some chemicals that is causing the polymerization. And that's kind of the other word that you always find in papers that deal with cell motility is myosin, right? So myosin is this chemical that's is responsible for this polymerization, and this chemical is diffusing, and so we have this parabolic equation for the phi with various parameters. The beta rho is what is the creation of this myosin, and so that's the active part, right, in this system that is very important to see the motion, any kind of motion. And the minus phi is the decay and the depolymerization inside the cell, right? So as I said, there's various models can be found in the literature that are variants of this. In particular, Berlion has done a lot of work on different models inspired by similar modeling considerations.
So all this is it's isotropic, right? So
yes.
How is this front and rear mechanism created?
So that's you're exactly right. So thank you for the question. It's exactly the issue, right? We have a system that is completely isotropic and suggests our experience with an equation like this suggests everything should be symmetric. And if you start, for example, from a cell that's a disk, there's no reason for that things to go left or right, right? It should stay where it is, and solutions, especially long time, should be symmetric, right? So, but keep in mind, and I'll go back to this, keep in mind that again, there's this active energy here, this phi, right? We'll see in a second as a destabilizing effect on the motion. Okay. And we will see, I mean, and that's sort of the goal. I mean, at the end of the talk, that's sort of the goal is to see that indeed a system like this can lead to this, what's called self-polarization, right? So this motion of a cell in one direction or another without having to put into the system any kind of, external potentials that would cause some anisotropy. Mm-hmm. So that will be the goal. That's kind of the point. All right. So what we have here, right, is a coupled system of first and second order parabolic equation. You recognize the first equation is a kind of Cahn-Hilliard type equation with the degenerate mobility here, right, the rho. Usually Cahn-Hilliard equations do not satisfy any maximum principle, but we know that when you have the degenerate Cahn-Hilliard, non-negative initial data gives you non-negative solution for all time, right? So rho should remain negative. It also preserves the mass, so the size of the cell is conserved. Typically, you would set these equations in a bounded domain with some kind of boundary conditions, right? So Neumann and no flux boundary condition at the boundary. Now, this equation is expected to be well posed, and I'm not going to spend much time discussing the existence of solution for this, right? But when epsilon is positive, well, one way to do it, so what we proved here with Alessandro Cucci and Nicolas Meunier, we proved the existence just in 1D using the basic tools that have been developed for the thin film equation, right? So if you forget about the W and the phi, what you have here is a thin film equation. There's a lot of literature on that, and it's not too difficult to prove the existence of solution. And if you add everything, then you can do a fixed point and you get solutions. If you forget about the phi, there is also a gradient flow structure that can give you solutions. Again, this is an equation expected to be well posed, although uniqueness is a completely open question, right? Even for the thin film equation without the W, without the phi, uniqueness is not proved currently.
Antoine?
Yes.
Can I ask a question? Mm-hmm. So you mentioned there is a term that sort of keeps the cell together. I didn't quite catch the details, but does it like keep it together, or it just a term that wants to keep it together, but it might still split?
So it will keep it together, and I'm going to discuss that actually in a second. Okay. So exactly, so you're exactly right? So what I claim, right, for now, is in this system, right, you have those two competing mechanisms. One is surface tension, and one is those protrusion. And so let me try to explain this a bit for for everyone, right? So especially for those who are not maybe familiar with those type of equations. So for example, if I forget about the phi, right? Forget the phi for a second, then what I have is just this Cahn-Hilliard equation, right? So if I take beta equals 0, there's no effect on the protrusion. And what I have is this Cahn-Hilliard equation. And this Cahn-Hilliard equation is a gradient flow for this energy, right? The usual modica mortala energy. And in particular, we know that when epsilon is small, right, this gamma converges to the perimeter functional. If maybe this one is a bit more classical, right? If you look at the classical Cahn-Hilliard equation with constant coefficients, so where you have just the delta, there's no more rho here, there's no more divergence of rho gradient, but just Laplace, right? Which is a gradient flow also for that same energy in h minus 1. Then that's a classical problem, right? When epsilon goes to 0, this thing converges to this two-phase Mullins-Sekirka type free boundary problem, right? In which you have a pressure that is harmonic away from the interface separating the two phases, and the pressure is equal to the, or proportional to the mean curvature kappa here on the interface, and the velocity is given by the jump of the gradient of the pressure across the interface, right? So that goes back to, I mean, Pego did this derivation, right, from Cahn-Hilliard to Mullins-Sekirka formally, and more recently, right, Les student of Serfati proved the convergence in the framework of those gradient flow, right, using the gamma convergence of the energy. We have a slightly different problem because we have, again, so we have this divergence of rho gradient instead of just Laplace, meaning we still have a kind of gradient flow, but with respect to the Wasserstein distance rather than the h minus 1 norm. And in particular, this means we have naturally, right, those solutions that remain non-negative always. And so in the limit, when epsilon goes to 0, this thing gives you a one-phase problem, or the so-called Hele-Show flow with surface tension. So now there's really just one set omega t instead of an interface separating two phases. P is still proportional to the curvature along the interface, and the velocity is the gradient of the pressure. So that's really the Hele-Show flow with surface tension. This again formally was derived by Glasner. And again, so this is a well-studied problem, the Hele-Show flow, right? We know that the mean curvature here is going to have a smoothing effect overall, and in particular, we can show that the disk is the only stationary solution for this problem, right? And if you start with a disk, you'll stay as a nice disk, and it's linearly stable. If you have a disk, you perturb it a bit, it will go back to the disk. So again, I'm talking about disk because we are typically in 2D right here for our cell problem, right? So this is for the part of our model that doesn't involve the phi, right? This is active potential due to the myosine. If I do the opposite, if I take back my model and I remove the surface tension part, so I remove the part, the Cahn-Hilliard part, right? So I take gamma equals 0, then I end up with, I'm left with something much simpler. Of course, I have just the divergence of rho gradient phi, that's all, right? And with phi solving this parabolic equation. Now, this is reminiscent of Keller-Segel type system with the chemotaxis, but the sign is reversed, right? So chemotaxis would be with a minus here, the usual chemotaxis, attractive chemotaxis system would be with the minus sign. So this is a repulsive type system, right? Where the particles are pushing away from each other. In particular, right, if you take in some limit here, if you remove the diffusion part, so if epsilon and eta here are very small, then you end up with rho that's very close to phi. And what you find is that this is basically a porous media type equation, right? And for this equation, there are no stationary solution, right? There's no stationary solution, regardless of your initial data. The support of the solution will always spread and never converge to anything stationary, right? So that's in that way that I mean that my original system, right, involves those two competing phenomena, right? The Hele-Show flow in some limit that wants you to get to the nice symmetric disk, and this repulsive potential that wants to spread everything as much as possible. Now, before I talk more about what we obtain, I want to mention another model, very closely related model that was studied by Berliand and his collaborator, which is a second-order model based on the very same principle. And so, but you have the same ideas. I mean, this is Allen-Cahn equation, right? Second order, but you have the same like flux due to the potential phi, and phi solves the exact same equation. Now, the second order equation does not preserve the mass, so they add a Lagrange multiplier for the volume constraint. And what they prove is that when eta is of order of epsilon square and epsilon goes to 0, those two things combine in a nice way. So Allen-Cahn type limit, right? So the Allen-Cahn equation, and the limit you get the mean curvature flow, not Hele-Show, right? You get mean curvature flow. But the effect of the potential, what they show is that it changes a bit the usual equation for mean curvature flow, which would be V equals sigma kappa, and adds this term, beta times f of V. Right? And when beta is large enough, they can prove that V minus the beta f of V is not monotone. And so that means that in this problem, the V is not uniquely determined, right? So this does not completely determine the V. And from a modeling point of view, I mean, from a mathematical point of view, it's a disaster, of course, but from a modeling point of view, this is good because it suggests that you end up with a model that is relatively unstable. And in fact, they prove that this problem has some traveling wave type solutions that move in one direction or another, even though, again, it's completely isotropic, right? You can have non-trivial traveling waves. And so, so our goal was to get something similar, of course, out of this fourth order type equation. All right, so let me explain a bit now what kind of results we can get in the limit epsilon goes to 0. And the first result, I mean, the first thing we did was to look at this, so our model here, and say, let epsilon go to 0. But fixing here, so eta, the diffusivity of the potential phi is fixed, right? I mean, of order 1. Now, this is important because we know that, I mean, the limit of the Cahn-Hilliard equation should give you a characteristic function. When epsilon is small, what you have here is a transition layer that has width of order epsilon. Right? And so here we are saying eta is fixed, meaning that the typical length scale of variation of the phi, right, is much larger than this transition zone, right? And so, and later, of course, we will want to see what happens when this is no longer the case. Okay, but in that case, the limit you can show is this Hele-Show, again, Hele-Show flow with surface tension, which is perturbed by this potential phi here, right? So in the condition for the pressure, at the boundary of the interface, you have, again, the mean curvature, but also this phi, and this phi now solves this simple elliptic equation. Right, so you can write the phi as a convolution, for example, if you are in Rn. This, I mean, the derivation here is quite simple. I mean, it follows the same kind of argument that was developed by Pego and Glasner for this type of problems. And again, I claim that this problem we obtain here, this Hele-Show flow, still has, of course, those two aspects, right? The regularizing of surface tension and a destabilizing effect of the potential phi. And this is very easy to see at the level of the energy. So this Hele-Show flow is a gradient flow for this energy, right? So you have the perimeter energy, that's where the surface tension is going to come from. And then this guy here, which is basically rho times phi, right? I mean, the characteristic function of omega times the phi, and which is the effect of the protrusion. And those two terms have completely opposite effect. And in fact, so we proved with Yijing Wu that when eta is small, so now eta small means you're starting to localize a little bit, right? I mean, again, if you look at the equation for phi, when eta is small, you're localizing the phi that's closer and closer to just being the characteristic function as well. So when eta goes to 0, if beta over sigma, now beta over sigma measures the relative importance of the protrusion of the destabilizing phi and the surface tension, right? So this is saying that you're increasing the effect of this potential phi over the effect of surface tension. So if this guy is of the order of the eta to the -1/2, And so if this ratio here now converges to some finite number beta, then for a given perimeter, this functional converge to 1 minus beta 0 times the perimeter. So, right, you still have, I mean, the 1 comes up to the perimeter, but the point is that this other term here, and I'm adding this constant that the limit is finite, right? But we're always working with things that have fixed volume, so we can add, adding the size, the volume of omega doesn't make a big difference here. The key is that this thing converges to minus beta 0 times the perimeter. So if beta 0 is between 0 and 1, in fact, we can prove that this is we have gamma convergence here of this energy to a multiple of the perimeter. But we see that when beta 0 is bigger than 1, right, what it tells you is that these things become close to a negative multiple of the perimeter, right? And so you're going to get something very unstable. Right? So for small eta, right, the conclusion is that here for small eta, the stability of the disk is really going to depend on the value of this ratio here, right? So and especially so the ratio between beta and sigma, so the importance of the potential phi versus the importance of surface tension. And this type of phenomena has been studied before. I mean, in particular, in the framework of the study of viscous ferrofluid in Hele-Show cells. So the idea is you have a fluid, the usual fluid in a Hele-Show cell, but in the fluid are some magnetic particles, and under some magnetic field, those particles are trying to move away from each other. And what happened is this type of things, right? So here is the first picture. So this is a numerical simulation done by Glasner. The first picture shows what happened if you start from a disk and you perturb it just a little bit, and you see for various time how those perturbations are amplified, right? So the thing is very unstable. The second picture shows a stationary state that is attained after some time, right? And so you see those fingers developing. Otto studied this problem rigorously in the limit where eta is small, like we were talking about, and with beta that goes to infinity faster than eta to the power minus 1. So it's much more than what we are looking at, right? Even more importance on the destabilizing potential phi here, and shows that in this case the dynamic is described by the porous media equation, right? So what he says is that basically in the limit you see this picture here, right? As in this limit those fingers become smaller and smaller, and so the characteristic function converge weakly to something that is no longer a characteristic function, right? And gives you a statistical description of where the fluid is going to be. And that thing is spreading for all time, right, according to the porous media equation. Now, of course, in that framework, right, the kernel is a bit different, right? You see this kernel here, 1 over x minus 1 over square root of 1 plus x squared. In fact, I mean, you can play a little bit, and we played with that with Yijing. So if we change the equation for the phi, and replace the diffusion equation by a fractional diffusion equation of order s over 2 here, I mean of order s rather, then it changes the energy just because it changes a bit the kernel that you're using. And then what we prove is that in that case, you also have gamma convergence to perimeter minus a multiple of the s perimeter, right? So the so-called fractional perimeter of order s, right? So this is s between 0 and 1, which means the Laplacian here is between the 0 and the Laplacian of order 1/2, right? Now, this is not as dramatic as what we had before, where we had really perimeter minus the multiple of the perimeter, right? I mean, the S perimeter is of lower order than the perimeter, but still, right, this type of functional has interesting dynamic. I mean, we can show that for a functional like this, right, there is some perimeter, I mean, some parameters, gamma 1, gamma 2, right? So that if this guy, beta 0 times CS is constant, is small enough, the unique minimizer is global minimizer is a ball. If it's a little bit bigger, the ball might still be a local minimizer, but it's no longer the global minimizer. And if it's even bigger, the ball is still a critical point always, of course, but it's not even a local minimizer, right? So we get something where the ball becomes very unstable. You can prove similar things without taking the limit eta goes to 0. So we have similar things for this energy with the non-local kernel here. And when S is between 1 and 2, well, you get something that's similar to the case S equal to, where you have perimeter minus beta 0 times perimeter, but the scaling that you need to use is a little bit different. It depends on the S. Okay, and of course you recover when S is 1, you have the eta minus 1 from the result here. And for mesis 2, you recover the eta minus 1/2 that I stated in the first result. All right, so all of this, right, all of this shows that we have clearly instability and symmetry breaking in this in this regime, right? So this is a regime in which, as I said, we took epsilon goes to 0 first, right, to get this phase separation. And then we looked at what happened when eta was small, right? So epsilon is much smaller than eta, much smaller than 1. However, in this model, we do not find any non-trivial traveling wave. So the self-polarization that I was looking for, right, the idea that cells could start moving in one direction or another, we don't see it here. So what we want to do next is look at the regime in which eta and epsilon go to 0 together. In fact, eta smaller than epsilon. I mean, the regime that works well is eta of other epsilon square. Now, the reason is because if you look at this, right, system, as I mentioned earlier, right, the Cahn-Hilliard regularization, you know that it's going to give you a transition layer of width about epsilon. And if you put epsilon square in front of the Laplacian of phi, then you expect the variation of phi to also take place over length scale of order epsilon, right? So now the two are really competing at the same scale. And in that case, what we show is this. So when epsilon goes to 0, and I want to insist, I mean, this is a formal derivation a la Pego, right? Which shows that the function rho epsilon should converge to a characteristic function of a set that evolve according to this free boundary problem. Right, so what's different here now? Well, we still have the Hele-Show type free boundary problem with a Q given by proportional to the mean curvature plus a term or minus a term beta f of v, which again, because of the parameter beta here, we know that it comes from this destabilizing effect of the potential phi, but it becomes just a function of the velocity, right? And the velocity is, of course, the usual Neumann derivative of the pressure. Okay, so this constant can be computed, of course. The key thing is that the function f, right, that we have here is a C1 function that depends on W, which is bounded and monotone increasing. Again, the proof use the same type of blow-up analysis and matched asymptotic method as the one developed by Pego. In the standard case, the difference, of course, being where we have to understand the derivation of this term. And very briefly, there's a definition of it, right? This function f is defined like this. You first find the psi, which is a usual transition profile for the Modica-Mortola type functional. And then you solve this ODE, right? For a given V, you solve this ODE that depends on the phi as well. And then you look at this integral, right? So that's your f. And this f we can show is C1 monotone increasing and has limits 0 and 1 at infinity, plus and minus infinity. When beta equals 0, this is a classical Hele-Show problem, right? There's no issue, right? So what I claim now is that when beta is positive, this problem has all the features that we wanted, right? It has, of course, linear instabilities, but also what's I call here hysteresis phenomenon and self-polarization. So the existence of non-trivial traveling waves. So I explained already self-polarization, this idea of non-trivial traveling waves. Let me say just a word about what I mean here by hysteresis phenomenon. I mean, those two words, hysteresis and self-polarization, are always mentioned again in the literature on cell motility as important feature of cell motility. What I mean is this, right? If you look at our model and you wanted to solve it numerically, right, what you would do is simply says that the pressure at time t is found by solving this equation, and for v here you would use the velocity from the previous time step, right, whatever velocity you had to get to where you are. But if you're not given that velocity and instead you're just given the picture of the cell at time t, right, so you know the set omega t and nothing else, could you still recover the pressure? And well, all you had to do is say, well, V after all is minus gradient of Q dot N. So I can just put that here and now try to solve this equation. And what I have is an elliptic equation with a nonlinear Robin type boundary condition. When F is linear, I know that this problem will be well posed if the A here, the coefficient is negative. In fact, this is used in the literature as a Hele-Show problem with kinetic undercooling. This typically is used to regularize the Hele-Show problem. And still works if you have, instead of a linear guy that is with a negative a, if you take f a monotone decreasing function, you still have a unique solution. But in our case, f is increasing. And so this problem is expected to be ill-posed. And we expect that, especially if beta is large enough, right? Knowing the shape of the cell at time t0, knowing omega of t0, right, might not be enough to know what is q and therefore to predict what's going to happen to omega, right? And this is what we call hysteresis. So it's the idea that in order to know where the cell is going, you need to know where it comes from, right? It's not enough to know where it is, because the history of the cell is important, right? So let me now show you a bit what we can say about our system in one dimension, because it's very simple, of course, and it gives us some idea of what we can expect to prove in 2 dimensions, which is the physical case. All right, so in 1D, things are a bit simpler, right? In 1D, there's no mechanism that can split the cell really here, so we'll say that omega t is always an interval. And the volume is preserved, so this interval has a fixed length. Also, in 1D, there's no curvature effect, right? There's no notion of curvature in 1D, so the equation is much simpler, and Q should be solution of this problem. There's no more kappa here, right? The first equation tells me that Q should be a straight line, so I write it like this: S times, yes, it depends on t, of course, times x plus a constant. And then I use this form here to, obviously the derivative, the normal derivative of q is just s of t, and so I can write the boundary conditions, right, coming from this. And now I ask myself, where can I find an s so that, I find a q of this form that solves this equation, this condition. And so if I put here, if I replace the q by this thing here in those 2 boundary conditions, I realize that this is possible if I can find s that solves this equation, right? So I have a simple equation, s times l equal beta times f of s minus f of minus s. And once I find the s, right, I'll find the q. And since the velocity, right, is the gradient of the pressure, the velocity will be just s, right? So this s will be the velocity of the cell. Now, the key picture is this one, right? It's not very well drawn, but is a black curve here, right? Is this function f of s minus f of minus s, which is an increasing function. And what I'm trying to do to solve the equation is find the intersection of this black curve with a straight line with slope L over beta, right? And you see that if this slope is large, like it is with this red line here, there is only one point, which is at 0. But if the slope is smaller, like in those blue lines, there might be 2 more solutions, right? And so what you can see is that there is a critical value, gamma c, such that if the ratio beta over L, so here it's L over beta, now it's beta over L. So if beta over L is small, right, which is a red line here, there is only one solution, which is S equals 0. But if beta over L is large, and again, beta over L is going to measure somewhat the importance of this destabilizing potential phi, right? If beta over L, there is at least 2 other solutions. You can do, so that's easy to prove. You can actually prove there are only 2 solutions if you take a specific, some specific form for the double well potential W. This picture here is actually obtained numerically, right, for the simple potential rho square times 1 minus rho square. So you see this bifurcation here, right? This critical value where you have this pitchfork type bifurcation. So for the original problem, well, what it means is that if your initial data is an interval, A0, B0, then if beta is small compared to this, the length of the interval, there is only one solution, which is a constant solution, stationary solution. Nothing is happening. But if beta is large, there are 2 other solutions with the same initial data, moving to the left or to the right with a certain speed c, right, which depends on the beta. Right, so we have those non-trivial traveling waves. Those are traveling waves type solutions, a fixed shape that's moving with a fixed velocity, left or right. Right, and again, the original problem has no anisotropy, and that's why actually the things can move left or right. You can also understand this as a type of hysteresis phenomena in the sense that the same initial condition can give you 2 different solutions, right? Or 3 different solutions. Of course, the asymptotic model that I wrote gives you no mechanism to say which of those 3 solutions you're going to see, right? So what this means, the way we have to understand this is that the epsilon model that I started from and which is expected to be well posed is extremely unstable. It means that for the epsilon problem, tiny variation in the initial condition might lead to a completely different type of behavior. Depending on very small variation in the rho epsilon initial, you may see this stationary solution, or you may see either one of those two traveling waves moving left or right, right? And that is exactly what we want, right? This is exactly the video that I showed you at the beginning of the talk. This is what we see, right? A very, very unstable behavior of those cells. We didn't explore this, but I think, this could be done rigorously in one dimension. It's not too difficult, but at least numerically, we can see that if you look at the epsilon problem, we can find those traveling waves. So those two traveling waves, they exist also for the epsilon problem. And I think, Berlion discussed this with him a little bit. He did something like this for his second order model, and believes that it can be done also for this fourth order model. That is using the fact that we know the traveling wave exists for the limiting problem, we can find them for the epsilon problem. All right, so now this gives us an idea of what is happening. Of course, the 1D case is a bit boring. There's no mean curvature, but it gives us an idea of what we can try to say about the 2D, two-dimension case. Right. Of course, it's more delicate. Now you have the geometry to take into account. And so let's start with a very simple question. If the initial condition is a disk, can I find the pressure? Right. So can I solve this equation? Of course, we have the constant solution here, right? So if I take Q equal constant, the disk is a stationary solution. But is it the only one? You can transform a little bit the problem by introducing this function phi, which is basically the stationary solution minus Q. And then you can reformulate the problem like this in a way that's more familiar, right? Because you have an harmonic equation with a Neumann condition that involves the Dirichlet data. So this is a type of fractional or non-local equation on the boundary of the disk. Right? In fact, you can introduce the Dirichlet-Neumann to Neumann operator on the disk, which is basically the half Laplacian in the torus, and write it like this. The function G, importantly, is monotone increasing. So we have a typical semilinear problem that we know might have bifurcation. And in fact, you can look at the linearized problem. You see that it has some non-trivial solution of the form cosine and theta for various for some values of lambda n, and then we can show that there are indeed pitchfork bifurcation for those lambda n. So if we go back to the original problem here, what it says, right, is that for some value of beta, those beta n, right, that are something divided by n, there are pitchfork bifurcation at which so we have curves of solutions, right, beta s. So I say pitchfork bifurcation because of these conditions here, right? So beta is beta 0 is beta n, beta prime is 0, and beta second is positive. Right? So that's a pitchfork type bifurcation, and the Q, which is solution of this with Q not being Q bar, right? So not 0. So you have this hysteresis type phenomena where even if you know that the omega, the set is a disk, you can't quite determine the pressure Q. There may be more than one solution. Again, this tells you that when, for the epsilon model, when epsilon is small variation in your initial data can give you very different type of behavior. We can try also to see a little bit what those Q looks like, what those pressure term will do, right? It's easy to see at the first order in S, those Q, they look like this. This comes from the solution of the linearized problem. And so the velocity associated to that is this guy, right? So cosine, basically, what's important is the cosine and theta. So it will create all those ripples, right? It will start it will push the boundary in all directions, makes those ripples. But if you look at the center of mass, right, the derivative of the center of mass in time, right, is going to be, according to this, right, in the first order of S, it's nothing for n larger than 2, but it's something for n equal 1. Now, this is interesting. If you look, by the way, at this, right, the value of beta, you see that I have a sequence of beta n for which I have those bifurcation points that is decreasing, right, in n. So I have a lot of bifurcations that are for actually small beta, but most of those bifurcation leads to just oscillations of the free boundary, but no macroscopic motion of the cell. Right? The center of mass remains fixed, except for the first one, which is actually the largest of all of the beta, and is this guy, so the R0 over F prime. for that one, we see that this hysteresis, right, tells you that even if you have a disk, you could have a pressure which is going to move the cell in some direction. Right? And then here, because I fixed everything so that things were only happening in the x direction, it's going to move in the positive x direction. But of course, we can do it in any direction. Right. And this, by the way, this critical value of beta, right, is consistent with the critical value we had in 1D. Right? In 1D, we had L, which is basically 2 times the radius, 2r0, divided by 2 f prime of 0. So it's the same value. So that's self-polarization, right? That's the idea that even starting from a completely symmetric initial data, we can have a macroscopic motion of the cell in one direction. Now the question is, if this happens, right, can we expect the cell to keep moving in that direction, or not, or will it go back and stop just a little bit later? And that is a question of whether or not there are traveling waves, right, for positive with positive speed for the asymptotic problem. Now traveling waves, right, for our problem are solution of the form omega 0 plus c times t, right, with a vector ex, the direction of travel. Right. So if I put this and that, right, that I want omega t to be of this form, if I put this and that into the equation, I get this thing here. And you see immediately that the first and last equation together, right, harmonic plus this Neumann condition tells you that Q plus Cx is constant inside the omega 0. So we call this constant lambda. And now you put this Q plus Cx equal lambda into the boundary condition here, right? And what you find is a traveling wave is a solution must be a solution of this problem, right? So you need to find omega 0 so that on the boundary of omega 0 you have this. Kappa being the mean curvature, so it's a second order equation here. And lambda is, I mean, you can think of lambda as a Lagrange multiplier for the volume constraint on omega 0. Of course, if you take C equals 0, the disk is a solution of this, right? Because C is 0, kappa is constant, so that's a solution. But we are interested in non-stationary traveling wave, of course. As I said, lambda, you can think of it as a Lagrange multiplier. Now, the original problem was completely invariant by translation. And you see that here, if you translate in the x direction, I mean, if you translate in the y direction, nothing happened. If you translate in the x direction, you will get a solution. You can find the same solution if you change the value of lambda, right? So you have to be a little bit careful with the lambda, because up to translation in the x direction, you recover the same solution with different values of lambda. Okay. But what we can prove is that for all, so if you fix lambda and sigma, there is a one parameter family of traveling wave, right? Parameterized by this beta, this coefficient beta, that has to be above this critical value, sigma over lambda f prime 0, with all of them positive speed. And when beta goes to this critical value, the speed goes to 0, and the omega, the set omega goes to the disk. Right? The set omega is always convex and symmetric with respect to the x-axis. Now that's just to fix the invariance with respect to the y direction. The boundary is C2 and we always fix that. So that's just to fix the invariance by translation in the x direction. We assume that the y-intercept, right? So when the point 0, y0, that's on the boundary of the set, we have a normal vector that is vertical. And at that point, we can check that the curvature is given by lambda over sigma. Now, this is interesting just because it shows that when lambda is increasing, the mean curvature at that point is increasing. And this suggests that increasing values of lambda will correspond to decreasing volume of the set that you're constructing here. Right. So the proof is completely constructive. The one thing that we are not able to do is, of course, go back from, so we do it here with fixing the lambda. We would have liked to then say that for a given volume, right, you can find a lambda so that you have a traveling wave here with that particular volume. And that we cannot do. Again, so numerically, we can check that this seems to be true, which is that the volume as a function of lambda is a monotone decreasing function. So meaning that for a fixed value of lambda, of beta, sorry, there is a kind of a maximum volume for which traveling wave exists, and then you can find traveling wave for smaller volumes as well. But so in particular, the one thing that we were not satisfied with here is that it doesn't clearly say what happens if you have a cell with a fixed volume and you're increasing the value of the beta, so you're increasing the strength of the destabilizing potential. And so what we can also show is a more bifurcation type result that says that now if you fix the volume, then you have this bifurcation from the radial solution from the disk at precisely that value. So that value at which, if you remember, this is a value at which we see this hysteresis phenomena gives you a pressure that might move the cell in one direction or another. So that same value is also the value at which we have the first traveling wave appearing with non-zero speed, right? And again, this same, so it looks exactly like the picture we had in one dimension, right? With the speed here as a function of the beta, the parameter beta. You only have speed 0 up to a certain point, and then you have those two speeds. I mean, you have those two branches, right, with speed s. Now, this theorem is nicer in the sense that it fixes the volume and it tells you what happened exactly when you are increasing the value of beta with a fixed volume. But because it's a bifurcation type result, it's local, right? It only says what happened in the neighborhood of this critical value of beta, and that's it, right? While the first theorem gives you a whole family of traveling wave for all betas bigger than a certain value, right? So together, so again, the theorem kind of construct two different, potentially different families of traveling wave, but together they really tell you that what you expect to find is that there is a critical value of beta, and by the way, those two theorems coincide for this critical value of beta. You get the same solution, the same disk, right? And so it tells you that when beta is large enough, the radially symmetric solution can develop a rear and a front, and then maintain this self-propagating motion, right, via those traveling waves. So this again is similar to the type of result that was proved by Berlian and his collaborator for the second order model, and more recently also for some other types of different but related model for cell motility, right? And this is really the type of result that people are after with these models, right? So, I mean, the conclusion of all of this, right, is that we were able to show that the asymptotic model has all the feature we wanted. It's ill-posed, it's terrible, but it's exactly what we wanted. We have we have instabilities, we have this hysteresis and self-polarization phenomena, and we have this critical value of beta, right, at which things starts happening. The expectation is that the phase field model for epsilon positive is well posed. We can prove it in 1D, and I think we could also, I mean, in some framework at least prove it in higher dimensions. It's not really an issue. Again, uniqueness is an issue, but it's a technical issue. It's not that we think the problem has more than one solution. It's just that we don't know how to prove uniqueness for this type of equation. But all of this tells you that when epsilon is small, the dynamic of even the epsilon model is extremely sensitive to small change in the epsilon data. Right? This is by no means the only model that has this type of behavior, but it is a very simple one, right? I mean, the asymptotic model that we write is very simple. Even the original model is quite simple, and so it's a very simple model that gives you, right, those behaviors that we wanted to see for cell motility. And I will stop here. Thank you very much.
Thank you, Antoine. It was a very nice talk. Is there any questions?
Can I ask a question?
Yeah.
Okay, so regarding this cell motion in biology, what is the most interesting question they want to understand? Like how, like if there's such one, like how this is could be say started through this model.
So I mean, I think, I mean, and that's what the mathematicians that have been working on this. That's kind of what we're aiming at. Is it's a very complex thing. There's many things going on, and so on the one hand, they have a lot of things are happening at the microscopic level in those cells. There's so many things. And they're trying to understand what is the basic thing, what is the simplest mechanism that you can say, explain this wildly unstable behavior and this sustained motion. I mean, this sustained motion in one direction is extremely important, right? The fact that cells can travel like this extended period of time in one direction is really a key thing in terms of what the cells are trying to do, right? And so that's all they want, right? They want to understand what is the basic feature, what is the basic mechanism, the simplest mechanism that can explain this, right? And so that's what all those models are doing, right? I mean, what Berlin has done and what we've done in some sense is trying to say, well, it doesn't have to be that complicated, right? You don't need a lot of things. You don't need a complicated system to get those behaviors, right? That you observe. This simple interplay, right, between surface tension and this repulsive chemopotential type things is enough to see those phenomena, this self-polarization and hysteresis phenomena.
Okay, thank you.
Anyone else? I was wondering why this, how do you interpret the fact that this only happens when you put eta equals, at least comparable to epsilon?
So, right, so I think, so the key thing, right, is why do we get, I mean, why do we have the velocity here, right? What is the velocity suddenly coming up in here? And I think the key is to understand this, right? Is the scaling, in terms of the scaling, is, again, in the first case, we had epsilon dt phi, right? So that disappeared, right? And we end up with an elliptic equation. Once you have this, though, right, because the variation, right, of phi occur now on the width of, I mean, on a scale that is similar, comparable to the width of the interface, the layer, the transition layer, right? The dt, right? The dt now is at the same order as this guy, and that's where the speed comes from, right? So this dt in the asymptotic expansion, this epsilon dt phi, right, which disappeared in the first limit because it was a lower order thing, is now at the same, appears now at the same order as the variation, the spatial variation. In some ways, you can say it's because in the first case, right, we ignore, it's almost like we ignore this term. And so at any given time, the phi was relaxed to, diffused and was relaxed, right? That's its equilibrium kind of thing, right? Solving an elliptic equation. While now, there is a kind of delay thing that's going on. When the cell is moving, the phi has to follow. If it's moving fast, right, the phi is not always exactly what it should be, because so the phi is keeping track of where the cell used to be, right? Because here the two terms, right, are of the same order, basically. Right, and so there's this delay in how long it takes the phi to follow the rho. I mean, again, when all of this is small, right, phi is equal to beta, I mean, phi is beta rho, right? So
you're saying that it has to be parabolic equation to
yes,
the chemical equation, okay.
Yes, so if I remove the epsilon dt phi, right, then I do not see this, right? This is for sure, right? But when I didn't have the epsilon square, right, this was negligible because the phi was smooth at the interface, basically, right? The phi was smooth, so it didn't matter. But now that the phi is no longer smooth at the interface, this really matters, right? And when the cell is moving fast, especially, you can see how the phi, which is trying to be like rho, is lagging behind, and that gives you this this term here.
Okay, thank you.
There's a lot of interesting question here after I mean, construction of traveling wave. A lot of the things we did here is rigorous, but in terms of limits, none of it is, right? So of course, nobody likes to prove the convergence of a nice system to a bad, I mean, to an ill-posed problem. But understanding a bit better how those properties of the limiting the asymptotic system translate into properties of the epsilon problem is interesting.
So it's not clear what features of the epsilon problem affects this movement, the direction of the movement, I suppose.
Right, but so I think that's the direction, the precise direction that the cell is picking is because of very small.
Right, but what exactly, right? I mean, we don't know.
I mean, of course, I mean, the cell is not, is in an environment where a lot of other things are going on, right? So the cell is constantly being pushed. I mean, in some ways you can say, what it's saying is that a tiny push in one direction or another will be enough to send it flying, for an extended period of time.
Okay, any other questions? Okay. If not, well, yeah, it was very nice. I have seen talks like where the instability is explained by non-uniqueness, but it was mostly about fingering. So I haven't seen this center of mass actually moving to one direction. And this is nice analysis. Okay, so should we then think, yeah, okay. Oh, someone just entered the room.
Oh.
Okay.
Time difference, sometimes it's confusing. Well, it was good seeing everyone.
Thank you.
Thank you for the talk.
Yeah, thanks for the nice talk. Thank you.
Yeah.
Thanks, Antoine.
Yeah.
It's interesting. People are coming.
Bye. Thank you. Yeah.